last time I gave some intuition of Dijkstra as like a water flowing through the network. There's going to be like another physical interpretation of things, and I think this might be even better. So you should maybe imagine that you have, let's say for now, undirected graph, okay? So that the physical intuition works. So you have undirected graph, G, and think of vertices as a ball, like a tiny ball of a point, and each edge is like a elastic, like a stretchable string that connect two balls together. Okay, so you can stretch it. And think of this picture where you put you fix the source node S at position 0, and like there are going down is 1, 2, 3, 4, and so on. Okay, and then you fix every other node at somewhere far away, like infinite. So right now, every edge is really stretched. Okay, and now think that suppose you now just unfix every node, every other node here. Okay, meaning that every stretched edge is now relaxed. Okay, and then you let the gravity pull vertices naturally. Okay, so what will happen? Now this guy will kind of go up, right? It was stretched. To go up, and so it might look like this. So if I ask you, once you let every string kind of stretch itself naturally, you don't fix anything. What are the position of every other nodes here? Well, it's going to be exactly what?
Whatever its length is, length of, so the distance from the source node.
Yeah, it's going to be exactly the distance from the source, right? A here, now it kind of hang around from S here. B is hang around from A, and the edge from A to B. Oh shoot, it should be from S to, yeah, the edge from S to B here. It's not stretched now because this is too long. It's not stretched. Yeah. Okay. And the one from S to C is now kind of tight. Yeah. So basically no edge will be stretched. Okay. And every node will precisely be at the position of its distance from S. And you can also see that the shortest path, the green one here is the one that is not stretched, but it's kind of tight. It's not, how do you call it? Yeah, it's tight but not stretched. This is the green one. And you can see that shortest path will be using only the tight edges. Yeah. If you're gonna never use the non-tight one because it's kind of go in the, it's not going in the shortest way. Okay. So this is a kind of nice physical process that gives you a intuition of shortest path, what it is. That is, just have a network of nodes and then fix S and then hang the network on the wall, fix S and see where are the position of every node. That's the distance to S. Okay. Make sense? Okay. And actually this physical process actually can motivate the algorithm too. So the way that you think abstractly might be you imagine that you have the real line, start from 0 and 2, and 1 and 2 and 3 and 4, right? And if I denote d of v to be the position of vertices, and I start a node S at 0 and every one at infinite, Okay. And what I'm gonna do is like I kind of try to relax edge. In the previous slide, I just relax every edge simultaneously and see what happened, right? But like right now, every edge is kind of like a stretch because here is like at infinity. We're gonna try to relax edge. And what does it mean formally? To relax an edge UV, it would mean this. We're just gonna put the we're just gonna try to ensure that the edge UV is not stretched by decreasing the position of V. Okay. So what do I do? Like I take the position of V and try to decrease it by how much? Just look at the position of U, right? If U is here, and maybe like this edge, and let's say like this edge was super stretched. So I gotta, but maybe like the edge length is maybe 2, and maybe this is like at position I plus 1, I plus 2, and so on. So we're just gonna like decrease position of V to here. And now an edge is not stretched. At least this edge is not stretched. This is what it means to relax an edge. So when you see like the word relax an edge in Dijkstra, this is really what it means, like to relax the stretched edge so that it's not stretched anymore. Okay. And basically you start with this and you can basically ask, okay, what kind of relaxation can we do on each edge so that at the end of the day there is no stretched edge left. And once there are no stretched edge, then you are basically at the point where you get the distance of everyone, just like in the previous slide. Okay. And if you think about it, if you like with this intuition in your mind, and you look back into Bellman-Ford algorithm, Bellman-Ford algorithm really just do this. Like repeat the following for n-1 round. And it just, for each round, just go through each edge one by one and relax each edge with this rule. This is what happened in Bellman-Ford. And there are like m edges. You can just go relax each of them once and repeat for n rounds. So that's why the running time is mn. Okay, but this is kind of wasteful because you kind of relax every edge like n time. And basically the idea of Dijkstra is that there's gonna be like the clever order of how you choose to relax edges so that every edge is gonna be relaxed once. And because every edge is relaxed once, then the running time is linear. It's basically linear. When I use tilde here, I kind of hide some log factor. Okay, like it means maybe there is like a log n here. I will use this notation, or polylog log square or something. Okay, good. So that's like the intuition of Dijkstra. Yeah. So once there are no negative edge, then you can relax every edge once. Okay, and what's the algorithm again? Like, it just start like what we do, right? Like put the position at s of to be 0, everyone at infinite. And now it's gonna like we're gonna do this. Just set like choose the kind of the finalized set to be like, okay, repeat until every node is finalized, and we just do this. Look at a node that is not finalized here, not finalized yet, and take the one that like has minimum estimate right now. Put this guy to your finalized set. And what we're gonna do is just look at edges incident to you, relax all those edges incident to you. So you're gonna decrease the estimate of like the guy that is incident to you, like decrease the estimate of V, and then repeat. Okay. So you can imagine what's going on. Right? We just like kind of keep relaxing edges, keep relaxing the stretch edges in some order. So you have seen and you are familiar with this. Actually, you learned it before, but today we're gonna just try to prove that this is correct formally. Yeah. Okay, so how to formalize this? Well, I'm just gonna need some concept. Okay, so F was the finalized set that we defined in the algorithm, and now like what we try to do is this. We will try to maintain this thing basically. That is, we try to make sure that our estimate D, the position of each node, or the estimate of the distance, is such that for every node that is finalized, then the estimate of that node is correct, is the correct distance. How about the one that is not finalized yet? The estimate of V is going to be something that is not quite distance, but is distance from S to V with respect to F. What do I mean by that? I mean, this is just the shortest length to go to V through F plus one more H. That is, F is like a ball around F. F is like the ball around S, right? And we're just gonna say that like this V to S to V of with respect to F is just minimizing over every node in F, like this maybe U, and take the distance from S to U plus one more H from U to V. Okay. And the key claim is this. So you see that like this is something that could be bigger than the real distance. Like it kind of restrict yourself to this kind of path where you go through the shortest path inside F and then take only one more edge. It doesn't look at all kind of path, right? So distance with respect to F can be more than the real distance. Okay. But now, okay, everyone in F have like we're gonna make sure that everyone in finalized guy have the correct distance, but the guy that is not finalized is not done, maybe not done. But the key claim is this. I want to say that, okay, this is not quite the real distance, but at least for the guy that is not finalized, but it has minimum estimate among not finalized guy. Actually, this estimate here is already this one. The estimate here is already correct. That is, for the not finalized one, the distance with respect to F here from S to U is already the real distance. That's my claim. Is the claim understandable, the statement? Question about the statement. All right. So basically, take the guy that is like kind of not finalized but closest, like but minimize the the estimate is minimized, then this is already like the estimate we have is already correct. Okay. So let's try to prove this. It's actually the key claim. So suppose that it's not the case, right? We're gonna show contradiction. So suppose that like this thing is actually strictly more than the real distance. Okay. If this is not equal, then it must be strictly greater than the real distance. Suppose that's the case. Then what does it mean? It means that like the shortest path from S to U, let's call it P, this shortest path must use at least 2 steps outside F. Right? Because if it can use just 1 step outside F to U, then this F here would be the real distance already. But here we said that, okay, this guy is strictly worse than the real distance. So the real distance, the real shortest path, must use at least 2 steps outside F. Clear? Yeah.
I guess I don't fully understand. So you're saying that the distance, so when you say the F set, the finalized set, it's 1 step outside of that finalized set to get to U. Why are we allowed to take that 1 step outside of the finalized set? Because I thought that U had to be contained within the finalized set for this to be true.
No. So like here U is outside the finalized set by definition. Like I said it, like look at U that is not finalized but has a minimum estimate. Now I claim that, okay, the guy that is not finalized yet, I have this estimate in, like I assume that I have this estimate for the guy that is not finalized. My claim is that this guy, U, not finalized but minimum estimate. This guy is already the same here. That's the claim. Is the statement clear to you?
Yeah, I think so.
Okay. And I'm just saying now that if let's try to prove this, that they are equal. Suppose not. Suppose for contradiction that is not the case. It means that this estimate for you is not the right distance yet. So it must be strictly greater than the real distance. And once, if it is the case, how can that ever happen? How can like this F from S to U is more than S to U, like this real distance from S to U? This is because this can happen only because, the shortest path from S to U kind of need to use more than 2 steps outside F, because like the definition of this F, distance F, is the shortest path that go to that node through F and just one edge, like 1 more step outside F. But this guy is first. So now it means that the real distance must use at least 2 steps outside.
Okay. The distance function, are the length of the edges the same in this case, or not?
Not the same.
So what if I'm confused on what if the distance to U, alright, like on the top where you have V to U, where it's only 1 step, like
From V to U here?
up, like on the top of the screen.
Okay.
Like 1 step versus 2, because 1 step's at the top and 2 steps on the bottom, right?
Yeah.
What if the 1 step is expensive? Like they call the 1 step.
It could be
cost.
expensive.
It could be expensive.
It could be expensive. That's why this one
Yeah,
can be worse than this one.
that one can be worse than that one.
Yeah.
Yeah.
I'm just assume that I maintain this invariant.
Okay.
If this is the case,
Yeah.
then I'm just gonna prove this right now. And later, I'm just gonna prove that we really maintain this invariant.
Oh, okay.
Yeah.
Thank you.
Okay. So back to the proof. Suppose for contradiction, if this is greater than this, everyone agree that like the real shortest path to you must kind of take 2 steps outside F. So there must be like let V be the first guy outside F in this path. That one is not you. Okay. V is not you. And so I can write down like this. The distance from this is the distance from S to U is the same as it's gonna be like distance from S to V plus distance from V to U. And this is just like the property of shortest path, right? Like when you kind of look at the shortest path and take like a sub interval of shortest path, you can just sum them up. Okay. But I claim that this thing is just the same as this of S to V sub F. Why is that?
Because it's taking a path that only takes one edge outside of F.
Yeah, it's by the choice of V. It's the one that it used just one step outside F. so these are the same.
Yeah.
Good. All right. So far, what do we have? We have this. Okay. Now I'm going to try to derive contradiction. Okay. So I claim that this whole thing is actually at least F of SU. And if we can show this, then we are done. Right? Because like you get this guy is greater than the same guy. So something is wrong. Kind of contradiction. Why is this the case? So I just gonna say that. Yeah. Basically, I claim that this one is greater than this, and this one is greater than this one. Why is this the case? Why, like, this F SV is at least this F SU?
Because how we defined it with U as the argument.
Exactly. U is the argument. U is the one that has minimum this F. That's our choice. So this one, U is the one that minimizes this F. So it must be like us, at most this F of V. How about this? Why this is like at least 0?
No negative edges.
Yeah, there is no negative edges here. That's the point. We need to use this fact at some point, right?
Yeah.
So we are done now. We get a contradiction. Okay. So among the one that is not finalized, the minimum estimate among not finalized guy actually have the real estimate, the correct estimate. Okay. Good. Question? Good. So
That would be best.
now we're gonna basically try to prove this loop invariant that we just said in the Dijkstra algorithm. Okay. So we have this pseudocode, and we want to prove this invariant. First of all, suppose that this loop invariant holds throughout the whole algorithm. You can see that then it means that the algorithm is correct, because at the end of the day, everyone is finalized, and we're gonna return our estimate D, but the loop invariant said that everyone that is finalized have the real estimate distance. The distance estimate is correct. So this loop invariant is something that is useful to prove. Now let's try to prove it. Okay, so let's try to say that, okay, at least after the first loop, then the invariant hold. Both invariant hold. And you know that after the first loop, what do we have? We have that f is gonna be basically just s. Like we're just gonna finalize at one node, which is f. Okay, and you can also see that the invariant would be correct because the distance, like for s itself, the distance is actually 0. So this is correct for s. How about everyone that is not finalized? We basically just relax everyone incident to s. So like you have s and all of s neighbor. Now the like if v is neighbor of s, then now d of v would be exactly the length from s to v, the length of this edge from s to v, which is exactly which is like distance distance f from s to v, right? For every neighbor of v, you get this one. Everyone is not neighbor of v, it's infinite. So the second invariant holds as well. All right. So now both invariant holds in the first loop. Now the next goal is like, okay, we want to say that the invariant keep holding after each next loop. If this is the case, then at the end it's gonna be true. Like everyone is finalized and we are done. We get the correct. So now let's try to say that after next loop, like assuming that the invariant holds for every step up to now, and then the next loop, they like both invariant will hold still. Okay. So okay. So I claim that after the let's look at the next loop here, and let's say we run up to here. Now the finalized set grow. Why would the invariant 1 still hold? Yeah, Scott.
Because of the property we proved on the last slide.
Exactly.
Since we picked the argument and we just proved that that has to be the actual, or the dist f has to be the actual distance.
Yeah. Just from the last slide, the key claim that we proved, right? We take u to be the minimum finalized guy, and the estimate of u is already correct. So even if u is now added to finalized set, this would be a correct one. So the invariant 1 is true by the key claim from the last slide. And the invariant, like the second invariant would be true as well because of the relaxation step. Why? So like for everyone that is not finalized, we need to update this f. How can this f change after we grow f by u? After we add u into the set f? This f can change only because of some path that go through u and take one step to v, right? And we do exactly that. Like we just update so that now the estimate of v can decrease according to like a distance that go through U and take one step to V. This is exactly what relaxation step does to make the invariant hold, the second invariant hold. Okay, so that means like both invariant holds through the next loop, and it's gonna keep holding until the end. And yeah, at the end we return D, and D is the real distance by invariant 1, and we are done. That's like the formal proof. Yeah. Question about this? Okay, so now let's try to think about like how fast this algorithm is, right? And we're just gonna use priority queue or heap for implementing this one. And priority queue is just a data structure, it's like an API that have some function for you, and you can call each of the function that it provide. What function does it have? So priority queue, you're gonna basically maintain a set. And what can you do with this set? The first function that you can access it is to insert. So to insert x with key k to the queue. So add x to the queue with value of x equal k. Okay. And next, what you can do is also to delete min. That is to find the element that minimize the value or minimize the estimate d. Okay, so that just delete x from the queue and return it. Find the minimum guy, delete it, and return this x to you. Okay. What else can the heap do? It can decrease key. That is, look at any element with the value k, then you just decrease the value of this element to at most k. You can decrease the key. Okay, and you can see that with this data structure, it really it's kind of built to implement Dijkstra. Why? So what you do here, in the initialization, you just insert, for every node, insert it with the value ds or dv to the queue, right? And to implement this, just delete min. It's just gonna give you the guy that is with minimum estimate. Just delete min. And now what you do here, you can do just by decrease key. Okay. So priority queue will basically contains all the nodes that is not finalized, and you keep decreasing its key, and sometimes you take the minimum guy out. Okay. So we're gonna call insert n time here, and delete min n time because that's the a number of loop we do. And decrease key, what do we do? How many times do we do in total? We call this basically sum over node, degree of the node, and that's OM. So that's the total operation that we call to the heap. Okay. And now it's just to finalize the running time. It's just about how fast you can implement each of these operations. Now we count how many times we call each operation. Now just count how to implement each operation fast, right? And there is a trivial way to implement priority queue, which is first way is just to use array, right? Just suppose we know that here we know that the maximum element there are just n element. So we just insert in one time, put it into that cell, decrease key, just update that cell, that takes all one. For delete min, well, if it's array, you just now need to scan through the array. That takes n time. So there are n insert, m decrease key, and n delete min. So the total time, if you use array to implement heaps, then it takes this much time. But you can do better if instead just try to implement priority queue with better data structure like a balanced binary search tree. Then everything you can implement in log n time, right? You just store it in like a balanced tree. The depth is log n. Whatever you do is take log n time. And so, like there are n plus m operation. So the total time is now m plus n times log n. So that's better. If the graph is not too dense, yeah, then it's better. And so today we now see like the correctness proof of Dijkstra with this running time. And later in class, like next week, we're gonna actually improve the running time to m plus n log n. We're gonna do this using a better heaps, like not just implement it using BS3, use something more clever. And to do that, to analyze this kind of heaps, you need to know more about amortized analysis. But that's for next week. Okay, so that's for Dijkstra. It's like a nice, really influential shortest path algorithm. And next topic, I will talk about dynamic shortest path. Okay. So this is like a dynamic single source shortest path, like Dijkstra. And the algorithm is called Even-Shiloach tree. It's like one of the most influential dynamic algorithm in the area of dynamic algorithm. Okay, so what's the problem? We're gonna look at simpler problem. For Dijkstra, we look at directed weighted graph. Here we're gonna look at undirected and unweighted graph to make it simple. So every edge has weight 1. And still use the notation m edges and n vertices like before. We have a fixed source. But now, instead of having a fixed graph, we have a sequence of edge deletion given to you. You start with the whole graph, and edge keep like disappearing one at a time. Like you don't know the whole sequence. Each deletion is kind of given to you one by one online. Okay, until the graph is empty. And what you want to do is like at every single time after each deletion, you want to maintain the distance correctly after update. Okay, good. So now the trivial solution for this problem is just that after each update, you just do BFS from the source, and that takes linear time per update. Okay. So in general, that takes like the total time then. Total time is then basically m squared, and that is like a n to the 4th inverse case. Okay. But what I'm gonna show you today is like you can do so that the total time is just mn, so better than m squared when the graph is dense, for example, and like which means that kind of the amortized update time, the average update time, is like a mn log n over m because there are m deletion. So that like on average, each update takes like n around n time instead of m. So that's better. Okay. Is the goal clear? Yep.
Sorry, where does m squared come from?
Oh, m squared come from like there are each update have this time, and there are many deletions because we keep deleting until the graph is empty. Okay, question about the problem? Good. So the algorithm is like this. We can initialize, let's say, in the beginning, you can initialize the estimate d tilde u to be the real distance. You just do BFS and get the correct estimate in the beginning. Okay. But now the graph can change. In the beginning, we are correct easily. Just do BFS. Now the graph can change. You can delete an edge UV. Like some guy just want to delete an edge UV. What we're gonna do is we're gonna call an important subroutine called update level of U and update level of V. Okay. I'm gonna explain what it does, but basically it's gonna do something. If U is not the source. If U is the source, then you don't touch it. If it's not the source, then you might touch it. And how exactly? Let's see the animation. Okay. So I'm gonna kind of try to explain the algorithm before going back to the pseudocode. Okay. So let's say that in the beginning you have this initially you have this single source shortest path from A, and this is the correct distance. So for every node, you maintain its level, basically, the level or distance, okay? And in the picture, the bold line is just an edge in the shortest path 3, but it doesn't really matter. Right now, we just care about distance, okay? But the point is if you delete an edge that is not a bold edge, then the distance doesn't change. If you delete an edge outside shortest path, nothing change. Only when you delete the bold edge, then you can change. Okay. But suppose now I delete this edge from A to B. Okay. And what we're gonna do is we're gonna call update distance at B because A is the source. We don't touch it. So now let me explain what this update level do. Maybe you tell me first what it is supposed to do. What level of B is supposed to be changed now? Yeah.
It's supposed to be 2.
Right. Yeah, because the shortest path from A to B need to go through C now, right? So basically what B should do is basically kind of okay. Now my shortest path, my level might change. So I'm just gonna scan through all of my neighbor, how I can connect to my neighbor in the best way. And the best neighbor of me is C, because C is the minimum level neighbor. So now I can kind of just hang around from C, hang down from C. So I update my level of B. Just look at all of my neighbor. Take the C because it's a minimum one, and put my level to be the level of C. Level of C plus 1. So that's 2. Okay. But now the level of B changed, and that could affect the neighbor of B. So B will basically inform all of neighbor of B that my level now changed, and all of his neighbor will try to now all of neighbor of B need to be careful now whether you need to update your level or not. Okay. Then in this case, one of the neighbor of B need to change. What's that?
E should change
E.
to 3.
Yeah, E should change to 3. So basically, E will basically just do the same. That is, E will now, okay, we notice that I need to update my level. And just look out at all of my neighbor, all of each neighbor, and set it to be like the level of the best neighbor plus 1. Okay, yeah.
How did F know to switch its? Oh wait, never mind.
Yeah, F don't switch. Yeah. So basically F is notified too, right? But that like the level of B change. But it still see one of its neighbor that is above it. So it doesn't need to do anything. C as well C is notified. But now C also see that okay, there is some guy that like is still above me. So it doesn't need to update. Yeah.
But F still did that like neighbor communication. Like it didn't update its level obviously, but it still like looked at its neighbors, right?
Yeah,
Okay.
yeah.
If you were to like delete an edge that did not connect to the source node, how would you know like which one to perform like that type of search first?
Try just do both. Yeah.
Like at the same time or just like one or
Actually,
the other?
Like you can do both, but actually there is a more correct, like less, like more efficient way to do this. That is, suppose you look at this one, right? And if you delete an edge that is between the node with the same level, then you know that this edge will not be in the shortest path for sure. So you don't need to do anything really. And if you delete, let's say, an edge between these two, one half level higher, one half level below, the higher one, you know for sure that it still have neighbor above it. So you only need to update the level of this lower level, like a lower one or worse distance guy. Yeah. Okay. Okay. So now E update the level to 3. And next E just notify all its neighbor that now my level changed. You need to be careful. But all of his neighbor don't need to do anything. So that's what we get after deleting A and B. Okay. And yeah, now like let's say I delete one more, delete A and C. Okay. So I just need to call update level of C. Look at all of its neighbor. Well, who is the best? Like it can be B or F. And now just set the level of C to be like the level of the best neighbor plus 1. So level of C is now is 3. Notify the neighbors. And now the neighbors try to be careful, like basically call update level of both of these guys, right? And what happened? Well, F doesn't need to change and B change. Yeah.
Can you go back to like when the one on the left? Yeah. So what would have happened if there was no edge from D to F and then we deleted this edge from C to A? Because then there's no path anymore, so they would just have like infinite level. How do we check that?
So you see that like they will keep like everyone will keep update level until like it go to like infinite. Or you actually know that once the level is more than n, then there's no connection for sure. So just set it to be infinite once the level is more than n.
Is there no more efficient way to do that than just like looping until one of them has level higher than n?
There should be like a way to make it more efficient, but if you aim just for mn running time, like even if you do this less efficient one, is fine. Yeah. But good question. Yeah. All right. So yeah, you just do the same thing. You update the level, like C update its level, so it's notify the neighbors, and then the neighbors update the level. Now F doesn't change, B change, and then B change the level, so it's notify the neighbors. The one need to change, and we are done. Okay, so this keep going. I hope you understand what's going on. Right. So in more detail, it's like just do this. When you want to update the level, right? Then if you're not the source, you do something. And what you're gonna do is this. Actually, the way that I'm gonna implement the algorithm is that I will just look at, like, I will maintain this thing explicitly. That is, you will look at all of its neighbor and kind of know what's the level of the best neighbor explicitly at all time. Okay, and the level of U is it's supposed to be this one, like the level of the best neighbor plus 1. That's like how my level is supposed to be. Okay, and now whenever what I'm supposed to be is actually now worse than what my current estimate is, it means that that my current estimate is wrong. Okay, so whenever this is true, then I know that I need to update my estimate. So I just update my estimate to be something that is correct. The level of my best neighbor plus 1. And okay, if whenever like my level now is like greater than n, actually I know that I'm even disconnect from the source. So I can just set my level to be infinite. Okay. And if it's the case that my level increase like this, then I notify all of my neighbors. Like all of the neighbors of you need to be updated. That's the algorithm. Okay. So a quick question is, which is related to what Scott asked, is like, look at the estimate of UVW. How do they evolve when I delete this edge? Right. So you see that like when I delete this edge, now you need to update its level. So it will just say that look at V and W, take like the level of me is like this level of U plus 1, so level of this is now 3, and now it notified the neighbor, and like level of V and W will be updated to 4 like this. This is, and then you will be updated to like, just keep toggling like that until it go to more than n, and you just say, okay, I'm disconnected. Okay. All right. So the way that I'm gonna implement is just, okay. Yeah, again, we're gonna just, for every node, right? As I said, I'm just explicitly maintain this number. My, like, the correct level that I'm supposed to be. Okay. And it means what? It means that like whenever the level of some node increase, then like we need to update the heap of everyone around it. Okay. So like if V is here and the level of V change, like increase, now like each of the neighbor of V, like a U here, U has the you maintain this number, this you prime maintain this number too. Everyone maintain this number of its own. So when d tilde of v change, like we need to kind of update the heap of everyone here. So that how much does it take? It takes like a degree of v times log n. That's the time to update the binary heap. Okay. So we're gonna keep this in mind for like for analyzing the running time. Basically, when we change the level of one node, we spend degree time basically. Okay. Let's try to see why this is correct first before analyzing the running time. So, okay. Basically, I argue that like at the end, like when after each update, when we stop updating, when we stop like updating our data structure, the estimate of everyone will be correct, will be this one. So this is supposed to be like the correct estimate, correct, like just the, d tilde of u will be just like the level of my best neighbor plus 1. And this is going to be true for every node. Okay. And why is that? Like, well, okay, there are two steps in the argument. First, if it's true that for every node u this is the case, then I like we need to say that then it means that this estimate is a correct estimate, is the correct distance, and that's the first step. The second step is to say that okay, our algorithm really maintains this thing, like, okay, and for the first step that supported that this is true for every node, then I hope you are convinced that like then it means that the estimate here is a correct distance. Just because like the estimate at s is just 0, and now like everyone just look at its neighbor, the best neighbor plus 1. Okay, so you like if this is the case, then it's a correct distance. And why is it the case that this is true for every node? The intuition is just that, well, whenever it's not true, okay. So I'm just gonna prove this now. Next, we're gonna argue that this is true for every node, okay? So after each update, I will claim that this is true. And let's see why this is the case. We're just gonna prove this by induction on time. So suppose that like we have this invariant until now, until the next update. Okay. And suppose that consider the time that this thing change. Like if this doesn't change, then like it's remain true. But how can this thing change? How can this expression change? Right? It can change only when edges change or this thing change. When some edge is changed or the level change. Okay? That is, it can change. For example, when we delete an edge, UV, or the level here change. But you know, like you say, like whenever one of these things happen, you just immediately update the level to guarantee that this thing is true again. Okay. So okay, again, from the perspective of you, from the perspective of the node U, this thing can change only when an edge incident to U is deleted, or like the level of its neighbor is changed, like increase. Whenever this thing happen, we just call update level of U. And when we call update level of U, it just ensures that this is the case. Just from the pseudocode, right? From the pseudocode, we just literally just check if this remains true or not. If not, then we just update the level to make this thing true. Okay. So that's it. Like that's the correctness. Question about the correctness. Okay. Yep.
So just to clarify, if we're deleting an edge that isn't part of this like tree that we've created, we don't need to do anything. Like
We don't need to do anything.
okay, yeah.
Yeah. And in particular, we know that like this expression doesn't change for any node.
Okay.
Yeah. So in the pseudocode, I still say that whenever we delete any edge, I'm still gonna call the update level at both endpoint. But we know that like when we delete an edge at the same level, like this is gonna be false.
Gotcha. Okay.
So you could just basically spend constant time to check that, okay, this is false, and you don't need to do anything. Yeah. Okay. More questions? Good. So now it's about the key thing, which is running time. Okay. So you see that most of the running time is just about like how many time we call update levels, how much time we spend on the update levels. Okay. And you see that when you call update level of U, and suppose that like you don't need to increase the level of U. Like for example, when you delete an edge incident to U when between an edge of the same level, you don't need to increase the level of U. So what you do is just to check the if condition there and just spend constant time. So if you call update level and don't increase the level, just spend constant time. But if you increase the level of U, you need to increase it. Then when you increase the level of U, you need to notify and update the heap of all of its neighbor. So that basically takes degree of U times log n. And here I just, let's say I exclude the time to recurse on the update level of neighbor of U, because that would be taken care of like I don't need to look at the time that I spend on the update level of V, because that will be taken care of when I analyze update level of V. So I separate that. Okay. So just to conclude, we either spend constant time or spend degree time, excluding the recursion. Yeah, that's okay. And now the key insight is this. The key insight is that, okay, the level of U can ever increase like n times at most. Because once the level of U increase to more than n, then you just set it to be infinite and never increase that ever. Okay? So it means what? It means that the total time that we're gonna spend on this subroutine, update level at U, this is gonna be the number of time that you increase the level, which is n, times the degree of u. Okay. And then so it means that in total, like when you sum over all vertices, it's just like this thing sum over all vertices, and that's like just sum over this thing. So that's summing over all degree is just m. So that's mn log n. Okay. So that's like, let's reflect a bit. What did we do? Okay. Okay. So if the total time is mn log n, so it means that amortized deletion time is this thing, the total time over the number of deletion. So on average, it takes n log n time.
So can you explain why we are sort of ignoring the recursion of use neighbors? Because even if it's like constant work, isn't it like let's say the degree of the node was n, and so even if it was constant work for each node, if there are n nodes, couldn't that still add up to like n work?
Yeah. So it's like good. So when you basically, okay, how do I say this? If this is u, and then look at v, and this is neighbor of u, okay? And if I said that I exclude the time that I spent on this guy, right? But why is that justified? So when you update the level of u and you increase u, you're gonna spend some time like calling each of these. So that seems a lot. But the time that you spend on update level v is either like constant or degree of v again. If it's constant, then you basically charge that constant to the time that you're gonna spend on updating the heap from u anyway. Like from u, you spend degree time on each of his neighbor. If this guy is gonna spend constant time, then it's gonna just charge to the time that you spend from u already. And if from v, you need to spend a lot of time that you update the level. I'm just taking care of that here. Yeah, make sense?
Yeah.
Okay. Right. But anyway, up to now we get now that like overall the algorithm, the total update time is mn, the total time that we ever spend, instead of m squared. Okay. But let's reflect on what's going on a bit, because you see that what we did is like we didn't try to bound the time that we spend per update. This is complicated because you see when we delete one edge, like there are some butterfly effect going on, like you update this and you update that and so on, and you don't know like how to bound the total time, like the time per update. But instead we kind of take a global view and say that okay, one single update you might spend really a lot of time, but overall you know that like every node, the level of each node can increase at most n time. And this is like a process that is true for when you think over the whole time sequence. So you take this global view and analyze this total update time instead of the time per update. Okay. And this is the point of view that is really basically central for amortized analysis. This is kind of the first teaser to amortized analysis. Next week is about amortized analysis. And in particular, I claim that actually one single update, you might spend this much time. Do you see some example? If this is S, and let's say like there are like a click here, like everyone connect to everyone. And now I just have one edge here, and I delete that. And now like basically everyone just keep toggling and like kind of take, like everyone keep updating is the level to end. Yeah. So just one deletion, you spend mn time. Yeah. But here we just said that, okay, one deletion can be very bad, but overall, you take mn time anyway. Okay. So just to make sure you understand, like I have some question. Suppose instead that I say that I have a graph and I keep inserting edges instead. Okay. I start with initial graph that is empty, and I keep up like insert edges. Can you maintain the distance like from a single source efficiently? What do you think? How can we do this?
So if we have an edge that like, let's say it connects like node that's at level 5 to node at level 1, then we'll need to update the node of level 5 to like a better level, so like level 2, and then we'll need to kind of cascade down in the same way that we did with the delete algorithm.
Yeah. So good. Basically, we just do the same algorithm. The same algorithm will work because just keep updating the like when you insert an edge at from A to B, just update level at A and B. Okay. It will be true, like you get the same correctness. But why is the running time still mn or mn log n when you only insert?
Because it can only decrease n times instead of only increasing n times.
Exactly. Like it's still monotone, right? Like if you keep inserting only every level only, like for every node, the level only decrease. And that can happen n times. When you decrease the level, you spend degree time. Summing over all nodes, that's mn. Okay. What if I promise that, okay, back to the deletion. What if I promise that the level, like the distance of from S to U to every node U is at most D? Why is it the case that like the total update time should be md now? I can improve from n to d if d is small. Anyone else? Okay, Scott.
Because now instead of only increasing n times, it can only increase d times.
Exactly. Like
Just replace n with d.
yeah, like I just promised that like every node can increase its level at most d time now. So the running time here is gonna be what? Like d, this is d, and that's like md log n. Yeah.
This is like just another clarifying question, but the log n comes from updating the heap for one node?
Yeah.
Okay.
In the homework, you will remove log n.
Okay.
Yeah. We ask you to remove it. Yeah. Okay. So next is that, okay, if now instead of we have only like we have unweighted graph. If edges can have weight at most w is a integer, Now, can you show me the algorithm that takes m and w time? Yeah.
Isn't it like the same idea where you now know like the upper bound is n times w because you can't go more than that?
Exactly. It's the same algorithm. You don't need to show a new algorithm. It's just you need to analyze that. Now you know that the level of every node is going to be at most nw, because if it's more than that, you know it's disconnected. So every node is update its level nw times at most. So instead of n, you replace it with nw. Now I claim that, okay, if there are both insert and delete, insertion and deletions, the algorithm is still going to be correct. Why is that? Well, this is kind of because you kind of ensure this at all time. We neighbor of you. And if this is the case at all time, then you are good. And we just keep updating levels until this is true for every node. So it's going to be true. It's going to be correct. But actually, the update time can be very bad now. Can be really terrible. Why is that? Yeah.
Well, before we were kind of bound by how many deletions we can do, or like if we were adding edges, you can only add so many edges, but now there's like infinite amount of things that can happen.
That is the case too, but let's say that I promise that before I can have like a m deletion. Let's say now that I'm gonna still do at most m deletion and m insertion at most, same number of deletion. But I claim that the update time can be very bad now. Yeah.
Well, so you mentioned before the case where it's like the root node with level 0 is connected to everything else with like it's a click, and then deleting that one delete is gonna be really costly, and then you can just like add that same edge and delete it and add it, and that would just be a mess.
Right. So yeah, in general, like the general perspective is that everything that we can bound the running time right now is because of monotonicity of levels. Like if you know that level only increase, you know that you're gonna spend time per node, like the number of time that you increase, and it's monotone, so you can count that you can bound the time, or it only decrease, so you can bound the time. But if you have both deletion and insertion now, like kind of the level of each node can go up and down and up and down, like all the way for every insert and delete. Like before we said that, okay, throughout the m many deletion, every node can increase or decrease at most, can change the level at most n time. But now it can be the case that just one deletion, every node increase the level all the way, or another insertion, every node decreases the level all the way. So that's a lot of time. The point is we kind of exploit monotonicity of levels in this analysis. Okay. But now I hope you see that, okay, if I still have both insert and delete, but I promise that insertion never decrease distance, then it's still fine. I just promise monotonicity to you. Yeah.
What does it mean to promise that insertions never decrease distances? Because I feel like if you insert a new edge anywhere and then end up deleting all of the other edges to that node, it will necessarily have increased distance at some point.
So, for example, if I look at my shortest path tree, and I promise that I'm just gonna insert edges only between two nodes with the same level, that never help creating any new shortest path. only like this edge is kind of still useless for shortest path.
But then if I deleted the edge, like let's say it's A, B, and C, if I deleted the edge from A to C, then that edge that we added would increase the distance, but just later. Is it okay if it does it like delayed?
Yeah, it's okay. It's really the case that like just from analysis, all you need is that the levels of every node is monotone. If this is insertion and it's useful later, but it's still monotone, like the level is still monotonic, monotonically changed, so it's still fine. Okay, so that's it. I have some of the, okay, let's see, let me go through like the state of the art quickly, because this is such a really important topic. It turns out that if you want to improve upon MN, you cannot. There is some lower bound, assuming some conjecture that I and my co-author introduced, and we kind of believe that. So you cannot improve upon MN. If the graph is weighted, assuming other conjectures, actually you cannot even beat M square. And M square is just a trivial algorithm, right? You can just do Dijkstra from scratch at every update. That takes M square, and you cannot improve that. However, if you now like okay with like some approximation, like you do like a 1.001 approximation, then you can do things much faster. Like some years ago, we showed that you can actually do it in total time, almost linear. So that's quite nice, but it's still quite complicated. And yeah, this area is still quite active, and I'm still excited about it. But okay, that's it for today. Next week, amortized analysis.